Hello everyone. Today we're talking about parameters and statistical correlation. And here, first a quick update in my presentation slides from last year. Now we have a new name in our university, so that's a little change there. And yeah, this is going to be a very exciting talk, I think, because we cover very important subjects. First, the parameter determination or estimation, rather. We'll look at the one particular type of parameter, which is the population mean, and how we can find, how we can calculate a sort of a interval that gives us an idea of where the value of a parameter may be. And then we will switch to statistical correlation. We look at a number of statistical coefficients that give us a sense of how correlated two variables are. And we'll also look a little bit, if time permits, the connection between confidence intervals and these correlations, these coefficients of correlation. So let's get started. The connection between the topics. I put a lot of animations here, so hopefully that makes it more entertaining. So let's see. We're going to start with parameters. So what is a parameter? Well, first of all, we have to think of having a population. Could be as simple as a population of individuals. It could be all the students at UMass, or it could be the population of a city, or anything we can imagine. Now once we have set this population, which has a size n, which can be a very large number, we can think of different parameters that we could calculate in this population. If we think of something very intuitive, we are thinking of height of individuals. That's a parameter, the mean height. So essentially, what is the mean height for calculated over all the members of this population? And we have a formula. Theoretically, we can say, well, the mean height, so the mean height across all the members of this population is, as you see in the equation, it's just the average from 1 to n of the height values of each member of the population. That's very nice, but how we calculate that, right? We unless the population is very small, we would need to take the height of each person in this population, which could be impossible. So how do we estimate the value of this parameter, in this case the mean height, for a population that is given and we are studying? Well, the way to do that is to use a sample. We take a representative sample of a size here lowercase n, which is much smaller than the uppercase n, which denotes the total size of the population, but still give us a sense or a good representation of what happens across the entire population. And we can say, well, if we have this sample, we can estimate the mean height by applying the same formula, but only over the sample. So that sounds reasonable. Now the question is, okay, we get this number here denoted by h var, which is the sample estimate for the population mean height, and that's fine as an example. Let's look at another example, maybe a little more relevant in the context of this class, which is about we could think of a population in this case of cells, and it could be a very huge number as before, and this could be cells of certain type, say cells in the lung of a patient, and we are studying the expression level of a gene in these cells, and we can wonder what is the mean expression level of this gene across this population of cells. Again, same problem as before. We cannot do this calculation over each each cell in the population, but we could take a sample. Maybe we have a number, again, much smaller with the total number of cells in this population, but something that we can actually observe and we can measure. And then we can do a calculation of this sample estimation. Now, kind of what is probably relevant, or at this moment we could think about is, okay, how good is this estimate? We have a number. It's like we cannot think of a point estimate. Is that estimate good, or we have a way of saying, well, given the variability in this population, maybe this estimate is not not very precise. How we get to how do we get to answer this question? Is there an answer? Yes, there is an answer, and we'll see how to do that. How to provide a measure of the let's say of how good this estimate is. So we have the idea is instead of just giving you one number, the idea here is to give a range of confidence. Okay, we are confident that the answer for this question, the population parameter, in this case the mean of a certain quantity, which could be the gene expression, it is contained in a certain interval. So we have that, the point estimate, just the sample mean, and as I said, this is not the best. We can do much better than just giving you this single number. We can do a lot better, and as I was saying, we can. It is actually possible to give a range of values where we could expect with an actual confidence level, with a number. If I want, if I say of I want to have a confidence of 95%. We'll see what that means. But if I want to have a confidence level of 95% of any other number, then we can get a range of values of confidence interval that we know within that confidence level that our parameter falls within. And this is called a confidence interval. And how we interpret this interval? Well, we have two things. A confidence level, let's say we want to calculate a confidence interval at a confidence level of 95%. And we will see how to calculate this interval. Let's say we have these two numbers that define our range of possible values for our parameter. Here I denoted them G min and G max, and it's our 95% confidence interval. We could have a 90% confidence interval, 99% confidence interval, but the method will be the same. The interpretation of this interval is that there is a chance, in this case 95%, that this confidence interval contains the true population mean. In this case, I call mu sub G because we are talking about the gene expression value. So you can think of this confidence level as a percentage of a confidence interval that contain the population parameter. So if we take samples of our population and we calculate different confidence intervals, if we have a 95% confidence level, means that out of, say, in this case, 20 samples from our population, 19 of those confidence intervals will contain the population parameter. So we might still get it wrong, but not that often. Just with a 5% chance of missing of generating an interval that does not contain the value or the true parameter value in our population. So that so far this might sound great, but how we actually do this? And in order to reach to the point where we can do that calculation, we need to talk a little bit about the normal distribution, the Central Limit Theorem, which are keys to do this. First, very quickly, refresher about the normal distribution. is the well-known bell curve. Here I'm in this plot. I'm showing the normal distribution with a mean of 0 and a standard deviation of 1, and there you see how those parameters are represented in the plot. And well, we can go a little further, and we can actually say, well, given the distribution here, well, there are important things to keep in mind when we talk about distributions in general, not only the normal distributions, that the area under the curve between two values of interest is the probability of observing those values in the population. And here, well, in this case, the values are 1.5 and 2.5, and that area under the curve is the probability of observing x between 1.5 and 2.5. And we can go a little further and consider, well, what is the density function here? The notation, without, I mean, I'm not going to go into lots of mathematical details. This is just a bit of a notation, but I won't go much further than this. You probably seen this formula. This is nothing else than the actual mathematical expression of the density function that is plotted there. And that's typically denoted when a variable x has a normal distribution with mean mu and standard deviation sigma. Typically, the way that is denoted, saying x and then that symbol, which the interpretation here is the distribution of x is such and such. In this case, it's a normal distribution of mean mu and standard deviation sigma. So the other thing that is maybe is good to kind of remember here is if we have a normal distribution that is not centered at 0 and does not have a standard deviation of 1, so it's not normalized, we can actually, with a very simple transformation, get a normal distribution with mean 0 and standard deviation 1, which is very simple. You subtract, if x is our variable with this general mean and standard deviation, we simply subtract the mean and divide by standard deviation, and there we go. We have a normal distribution centered at 0 and with standard deviation of 1. So, okay, this sounds, well, I'm sure you've seen this already. And the other distribution that will come up in this lecture is one that is almost normal. It's a distribution that is called the student's t-distribution. And this distribution is a distribution that depends on a parameter n called the degrees of freedom. And these distributions approximate the normal distributions as n grows larger. You see here that starting with n equals 1, 2, 5, and then a very large n approaching infinity, then we get a curve that is indistinguishable from the normal distribution. And this, I mean, one interesting fact is why this is called student. Actually, I looked it up on Wikipedia, and it's apparently one of the mathematicians who wrote about these family distributions did that publication as under a pseudonym, student. I don't know the reason, but that's kind of why these distributions are known by this name. So, but now the question is, okay, normal distributions are everywhere, right? That's kind of our, at least our, if not intuition, is what we've heard, no? Like height is normal, or you know, to start with, but any other type of variables that we can observe in the world around us has a normal distribution. It's not really, I mean, it's not really that much, or I would say that was so kind of surprising to me. But if we start looking a little deeper, there are many types of data that do not have a normal distribution. They deviate from a normal distribution, and that happens across many domains. This is a citation from a paper on psychology, and there they look typically at things like education or you know, responses to surveys and things like that. But there they have this observation that many of these data are not normal. And in fact, there was this interesting paper back from, I think, '89 here, that they looked at that problem. Well, not a problem, it's just a fact that maybe might run counterintuitive, but normal distributions are not that normal in a way, but they are very important. This also happens in transcriptomics. If you start looking at genetic data, even more than half of the distributions don't have a normal, are not normal. And this is also a reference that I have included at the end of the paper, of the lecture, if you want to look into more detail. So there could be a lot of different distributions. The normal distribution is just one possible distribution we can have characterizing our data. You can have this Cauchy distribution, which is kind of has a more pronounced curve, a log normal, which is not symmetric, a Pareto distribution, exponential, a gamma distribution, or even more unusual things, if you will, like with multiple modes, or not kind of with a single maximum. And yeah, looking into kind of this I was looking a little bit more into, what is in the literature about normal distributions. About this paper also from a few years ago, looking at cancer transcriptomics, and they're comparing these distributions and how they differ from normality. And that happens more often than we might in principle expect. And here in these plots is in this kind of, here you have 4 different data sets, and showing in red kind of the bell curve, and then the histogram from the observed data. And kind of in that inset, you see this other plot you might already learn about, which is called a QQ plot, and it allows to compare 2 distributions. And if we compare our empirical distribution from the data with the normal distribution, and both distributions are very similar, then you would have a curve that falls along the diagonal. And you see here that the curves that come from the observed distribution, which is kind of that curve in red in the 4 insets, actually deviates. It doesn't really fall it doesn't follow the diagonal that well. So that's a way of kind of showing, these distributions depart from normality. And so, well, if normal distributions are not so normal, why the normal distribution is so important? And well, there are many reasons. Here we are particularly interested in with the whole story of population parameters. How do we estimate confidence intervals? And then we have a very powerful tool to calculate those confidence intervals, which is really kind of an amazing result from the field of probability, which tells that if we have a random variable that we're studying, doesn't matter what the distribution of that variable is. Could be anything. The distribution of the sample mean gets closer to a normal distribution as the sample size becomes larger. So it doesn't matter. In a way, everything converges to a normal distribution. Here we're talking about specifically in the context of calculating the sample mean. In essence, this is kind of this result, or this conclusion, is thanks to the Central Limit Theorem. And what exactly means more kind of graphically is that, let's do an example where x, our variable of interest, is at the expression level of a gene, and it doesn't matter the distribution of x. Could be exponential, could be multinomial, and the thing is that if we take now the sample mean, that new variable, because now we have this x var that we calculate by taking a sample size n and calculating the sample mean, that's a sample variable, because every time you take a new sample, you have a new value. So what happens is that, well, first of all these n variables are, if you think about it, they're just copies of the same underlying data. We are just making n draws to construct our sample. We are just making n draws from our population. So it means that each one of these variables, x1 through xn, are equally distributed because they come they come from the same population, and they're independent. Assuming, of course, there are some assumptions here that we are not getting to the details. But if the observations are independent, then we are in this situation where the central limit theorem applies. And what happens is that the distribution of this new variable, x bar x hat, is actually normal. It doesn't matter if your distributions in the population are, could be anything. The sample mean as a random variable will have will approximate a normal distribution as n grows. And n doesn't need to grow. N doesn't need to be like 1 million. Typically with n, the conversion is pretty quick. So the rate by which the sample mean gets closer to the normal distribution is quite quick, and by n equal 30, typically that's enough. You might have, this is something that, and this is actually the central limit theorem in a way. You have n random variables equally distributed and independent, and their mean of those variables, which is a new random variable, will have a distribution that gets closer and closer to the normal distribution. So what do we do? Well, I'm going to reemphasize that because it's very important. A big goal of this lecture is to really make you aware of the importance of the central limit theorem and how we use it to calculate confidence intervals. This is the thing. It doesn't matter what the original distribution is. CLT ensures conversions to normal. And very quickly, the disclaimer. As long as the condition of having independent and equally distributed variables apply. So that's also important. And more formally, we can write it more mathematically. Again, I promise I won't go into a lot of equations, but it's good to have this in mind that, okay, if we write the distribution of x hat, which is our sample mean, it follows a distribution. This is more precisely what it means by that approximates a normal. That the distribution of x hat becomes very close to a normal of mean mu, which is the mean of the population mean, the true population mean, and sigma square divided n. That's as the variance and of our distribution. And that's interesting because actually, if you look at what this is saying is that we take, the mean of this normal distribution is always is the population mean. That's what we want because we want to approximate the sample mean, the population mean, with our samples. The other thing you can get from this is that as we take n larger, the variance tends to 0 because n is dividing. So it means that we are getting progressively more narrow normal distributions. Right? So again, sigma, remember, is the standard deviation of the population, but for each one of these normal distributions, for each n, and n grows larger, this is the standard deviation, not the population, but of the sample means, which becomes smaller and smaller, which makes sense. As we grow our sample, you think about it, what's happening, we have less uncertainty about our mean. So that's kind of embedded into the formula for the variance of this sequence of normal distributions. In particular, we could, if we normalize, as I mentioned before, if we have a normal distribution with an arbitrary mean and standard deviation, we can, by doing this normalization, we get a normal distribution between 0 and 1. So what do we do with this? All of this is quite nice. Let me show you before going. So again, I want to really delve into the importance of CLT and how we get always a normal distribution no matter what. And here is a little example with code where let's start with something that apparently is very different, right? Let's start with an exponential distribution. So you will say, well, this has nothing to do with the normal distribution, right? The normal distribution is a bell curve. The exponential curve is a it's a steadily decreasing curve where doesn't seem to share much. Typically, the way you say this is that x, so x has an exponential distribution with parameter lambda, And the formula is very simple, actually. It's lambda times the minus the exponent of minus lambda times x. This distribution has only one parameter, and actually the mean and the standard deviation are the same, which is 1 over lambda. So how we're gonna do here is I'm gonna create samples. So I'm gonna create, like, it's a kind of simulation example. I'm gonna show how by simulating a population that has an underlying distribution we know, which is exponential, and then we draw samples of increasing size. We'll see how the histogram of those samples of the mean, the sample means taken from this population, they will look very. The histograms will look very similar to a normal distribution. So we start. So let's. I mean, this is a simulation in the sense that I'm gonna define the parameters. So I'm not creating. I'm not looking at some observed data, but I'm gonna generate my own data. So let's say that my population has a mean of 130, and I'm gonna start with, here I have my parameters. So this is our code that you could actually type in RStudio and run, and you should be able to get the same results. And well, this is our sample size. Let's say our sample size is 10. Let's start with something small. And okay, because our population, I'm saying the population mean is 130, and in the exponential distribution, the population mean is inversely proportional to lambda. Then means that the lambda is 1 over the population mean. And then we need another number, and we need another sample size. And why is this? And this is 1,000. What's going on? Well, we need to look at the distribution of the sample means for a given n. So imagine, okay, we set n equals to 10. So we are looking at sample size 10, and what we know from the CLT is the distribution. The distribution of that random variable, which is x hat, it will approximate a normal distribution. Maybe not too much yet because n is not too big, it's 10. So it means that we need to construct the histogram of that random variable, x hat, for this sample size. So we need to draw, what we need to do is we need to generate many samples of size 10, and with those many samples of size 10, which in this case is 1,000 samples, we'll get a histogram. And that histogram should be similar. We can compare. We will see how it is, but hopefully it won't be too different from a normal distribution. So I'm going to put all these values in this list. So essentially what I'm going to do is I'm going to run a loop to sample, to draw samples of size 10 in this case. So, well, this is, we can do it very easily. We have a function in R that given the n and the lambda, which are the parameters of our exponential distribution, we get a sample, and it's a sample of size n. And then what we do is to calculate the mean. So here with the function mean, we are essentially we're just implementing the equation for the sample mean. So that's all that is doing. So we have m, this number m. So this number m is one realization of our sample mean. And so what we do is we put these values, we just keep storing these values, and we'll have 1,000 because we have the number of samples for our histogram is 1,000. And with that, we should be able to plot. So now we have, we collected our data from our simulated population. And then what we do next is we simply, we put that in a data frame. So mvals, remember, is the list of values that we simulated, and then we plot. So we want to plot two things. Okay, that's we're using ggplot here. I think you've been using it already, and I'm gonna plot two things. I'm gonna plot the histogram, and the histogram will come from the data frame, and it's a histogram. So there I have to say how many beans and the color, and then I want to plot the distribution. I want to compare my histogram with the normal distribution. So yeah, that's all that it is. And here we can see these different for these different sample sizes how the histogram gets really closer to the normal distribution it's approaching to. And this is for n equal 10. And it's already not that bad, but I mean, if you pay attention, you see that it's not perfectly symmetric. You see that there's kind of a little more empty space under the curve, and the red curve is the plot, the normal density. You see there is a little more empty space on the left side than the right side, and if we take 20, it's already much. I mean, there's obviously there is noise. There is noise here, and we could reduce the noise in the histogram by taking a sample, a larger histogram sample size to get a better histogram that better represents the distribution of our sample mean. So there are two things going on here, but you see that I mean, it seems that once we reach 20, I mean, might be a little better perhaps for 100. I think it's, you know, here what is happening is we have our histogram also that introducing noise. But you see that we should get closer to the red curve, and indeed it's happening. And we started from an exponential distribution, which is very different from normal. That's quite fascinating, I think. And you can actually play with this interactively. There is this really nice online book on probability and statistics that actually has a section on the central limit theorem, and you can actually do what I just shown, you know, with this one case with the exponential distribution. But you can do it kind of by controlling some sliders, some parameters. You can actually generate different distributions and see how the histogram of the sample mean is always something that resembles pretty well a normal distribution. So I recommend this. There is also, well, I think people have recommended this video YouTube channel that has great videos on all kind of topics related to statistics, and obviously has one on Central Limit Theorem. The link is there. So yeah, many resources that you can use to complement what I've said. Okay, fantastic. This is fascinating. Okay, there is something really almost, you know, it's kind of very profound result, I think, in how random variables, when you calculate a sample mean, they tend to be, they approximate very quickly a normal distribution, even though they could be something very different from a normal distribution. How do we use to construct the confidence intervals? Because that was our original problem, right? And so the idea is to, as I mentioned before, we start with a confidence level, let's say 95%, and how we connect things? Well, we have in our normal distribution, we have the area that under the curve. So we have this kind of given a confidence level, we can calculate these values that correspond, that give us the area under the curve being 0, 95, and the critical values, which are here, it's called, well, z, in this case, is alpha. So essentially, kind of a little bit of a reciprocal term. Here we start with a confidence level, 95%, and we will take the significance level alpha of 0.05 to find the critical values corresponding to that alpha, which is, you know, each, because we are taking, what we want is that the probability outside of kind of the center of the curve, that would be 0.05. And so on each side of the curve, we want to have 0.25 as the area, so that's why we have alpha over 2, and we have the critical values. So all of these pretty standard in terms of calculating these critical values, and we can do that pretty easy in the code. And the critical values for a significance level of 0.05 are 1.96, and we have on the two sides, right? The negative and the positive side. And what do we do with this? What do we do with this is that, well, we know then, based on this result, that if we take the normalized, so if you are thinking of the x hat, but we normalize it, we know that the probability of the normalized normal random variable so the probability that our normalized variable is between these critical values is 0.95. So here what we have is essentially we can reverse this. So essentially what we're saying is that, okay, the probability of getting the normalized variable z, what I call z before, which z is defined x hat minus the mean divided the standard deviation divided the square root of n. This was given a sample size n. The probability of getting that between between these two critical values is exactly 0 and 95. That's the definition of the critical values, right? Meaning that the probability of getting, if we take this inequality and we leave, we kind of solve for mu, for the standard, for the mean, means that we will get this inequality. We are just moving around things. We are subtracting x hat and then multiplying by sigma divided square root of n, and actually we have an interval here. We have that if we calculate that interval, we have a 95% probability that mu will be there, the population mean. And the problem here is that we don't know what sigma is, right? Because we want to determine. I mean, remember what is the problem? We take a sample, right? We take a sample to estimate the true value of the population mean, which is mu. And but in this calculation, okay, we get these two intervals. Great, but those intervals depend on sigma. We don't know sigma, so how we get out of this, right? And well, that's where the student's t-distribution comes handy, because well, we don't know the population standard deviation, but we can estimate it. Similar as we did before. I mean, the estimation, the sample estimation for the population mean, we have it, and it's very similar. So we have a formula for the sample standard deviation. Now, one thing to keep in mind is that we have n-1 there. So that's to remember. That is different from the population standard deviation, where it's just 1 over n. Here we have n-1. There are reasons for that, but it's not, that's outside of the scope of this lecture. So we have a way of estimating. The problem is that if we use this kind of estimator, if you use S instead of sigma, the distribution of this z-score, this z variable is no longer normal, but now it's a student's t-distribution with n-1 degrees of freedom. So that's how how the student's t-distribution comes into play, because we are actually, we cannot use sigma because we don't know it, but we can estimate it. But if we use the estimated value, the distribution of the z-score is not, now it's a student's t-distribution with n-1. And you see there, the n it's connected to the sample size. And so essentially what we have, instead of this, right, because this is kind of, if we know the standard deviation of the population, if we don't know it and we replace it by the estimation, the sample standard deviation, we have this being closer to student's t-distribution with n-1 degrees of freedom. So we eventually arrived to this formula. So putting all of this together, we have this interval where now we have all things we can calculate, because x hat is the sample, the mean, our estimate, our point estimate. But now we're adding these, the two kind of the minimum and the maximum. So we have this range of possible values that can contain our true population mean, and the standard error is simply the sample standard deviation divided by the square root of n. And now the critical value here, because we are not longer talking about the normal, we are talking about the the student's t-distribution, we have the critical value for that. So yeah, that's all we need. And I'll show very quickly, well, first of all, there are a couple of rules here, because these results are all kind of asymptotic results, meaning that things tend to something. If your n is too small, we're in trouble. And this other thing I didn't mention. If our observations are normal, the sum of normals is normal. So if we know that if the population has a normal distribution, if the parameter in the population has a normal distribution, then all of these sample means have a normal distribution as well immediately. So we don't have to do anything really. So the thing is that this is a little bit of heuristic. It's not, I guess, typically it's based on experience, let's say. In most cases, if the sample size is 30 or greater, nothing to worry about, because we are already very close to normal. You saw that how things converge pretty quickly, and the observations do not need to be normal. If we are kind of intermediate range, things might be deviate from normality. So if we don't have a sample size that is too big, we should better make sure that the observations, the data comes from a normal distribution to be able to apply the formulas. And finally, if we have our sample size is too small, unfortunately, we cannot do much. We need to use other methods that, again, are outside the scope of this lecture. So, yeah, I think I'm going to do a very simple example of a confidence interval calculation, again, with some R code that is easy to replicate. Here, I start with a sample, so I have a vector of that is my sample. Could be, values that you have from experimental data. You put them in this list, and then we have our sample size that we calculate as the length of that list. And we set a confidence level, 95, and then we get the alpha, which is 1 minus confidence level divided 100, because we are going into the kind of the reciprocal number, which is the significance level. And then we get the critical values. The critical values, how we calculate, there is a function that gives us just that for the student t distribution, where we just give the interval we want the critical values for, and then we say the degrees of freedom you see there, and then we have the critical values. Those are the critical values, and here we are at n equal to 30. Our student's t is pretty close to normal. There is a little bit of deviation if you look closer, but not too much. And what we need? Well, we need the sample mean. We calculate there. We calculate the sample standard deviation, and that has the right formula. So we don't need to worry about putting n minus 1. The SD function in R will do that. And then we calculate the standard error, as we saw before, the formula. And then we have the confidence interval, the lower bound, and the upper bound. And there we go. So now we can print our result, and the 95% confidence interval in this case, given this sample, is 108 and 138. So the calculation is pretty simple. What you have to be aware of is these rules to make sure that you're applying the calculation when it's possible to do it, and that depends on the sample size. So I'm gonna talk about I think we could go for hours with Central Limit Theorem and all these details we kind of skimmed through. But hopefully this gave you an idea of how we go from we want to estimate a population, a parameter of a population. In this case, we are specifically interested in the mean. And we, by applying this very special property of the distribution of sample means, we get to a formula that allows us to get this interval. Now, there's a connection, another very interesting connection between this concept of confidence interval that we just learned, and another very important concept that you will see in more detail in the next lecture. And I want to start drawing some parallels. Manuel will go deeper into this, but I think I can start because we already have the concept of confidence interval. And you might have probably heard about hypothesis testing. I'm going to kind of jump ahead a little bit. This is for tomorrow's lecture, but and some of you might know about this already. And the idea is that with the hypothesis testing is that we have two theories. We have two theories. We want to pick one over the other. So we have a null hypothesis, which kind of where there is no effect. We have something like our default, and we want to make an observation. We make an observation, and we want to based on the observation, we want to keep our null hypothesis or reject it and adopt an alternative hypothesis. So again, we are here in the context of a situation here that we could consider something like this. We have a null hypothesis, which is we have a population, let's say, that has a normal distribution, and we want to determine if the normal distribution, if this distribution has a mean that is 0. That's our null hypothesis. Let's start with our kind of null hypothesis that assumes that the mean is actually 0. And the alternative is, well, it's different from 0. It's kind of the negation of our null hypothesis. How we do this? And well, I mean, if you think about it, if you make an observation, the observation that you make is not very consistent with the null hypothesis that is telling us, well, the mean is 0. Imagine that, okay, if the mean, if the distribution is truly a normal distribution with mean equals 0, you should get, when you draw a sample, you should get something that is not too far from 0. But if we get something that is very different from 0, then we could, with certain confidence, we could say, well, actually, maybe we could reject the null hypothesis. We might be wrong, but with a certain confidence, we can make that decision. And again, here, see how how things are very deeply connected, or it's kind of one thing one thing is a version of the other. So here we think in hypothesis testing of a significance level for our test. And essentially, if we take a sample here, if we calculate a sample mean that falls outside the region in where the distribution has a probability of 0.95, it means that getting that value is not very likely. It's actually 0. The probability of that happening is 0.05. So you can conclude, well, with a 0.05 probability of being wrong, I'm going to reject the null hypothesis. So the observation, in this case, the sample mean has a probability of 0.05 of happening, so we reject it. But it might still be the case. You might still get a sample mean that is quite far from 0, even, but it's just not very likely, right? So how this connects with confidence, that's hypothesis testing. How is it connected with confidence intervals? Well, the connection is kind of quite, you see that we are saying that if we give a confidence level, what do we do with confidence intervals? Well, we have a confidence level, which is kind of the reciprocal of the significance level, and we calculate an interval that is likely to contain the parameter's true value. What is the parameter we are interested in is the population mean. So again, we have the same thing, and we can calculate if we give. So think what we did before. If we calculate a sample mean, we can calculate with our formula before. We can calculate a confidence interval. And if that confidence interval doesn't contain the value that we are assuming that is kind of the null hypothesis, then we might that's when we reject the null hypothesis. But it's kind of the other side of the side of the coin, so to speak. Getting a confidence, getting a sample mean that is outside of those. That area in the distribution, or kind of that range in the distribution, is the same as getting a confidence interval that does not contain 0. So it's kind of a duality there. And the interesting thing, I'm going to put a kind of a long quotation because I found this very interesting. And again, Manuel will give you some more materials to read about hypothesis testing and why sometimes what is called the p-values, kind of the 0.05 here, the p-value of the observation is yes or no. Okay, we reject or we keep the hypothesis. But with a confidence interval, we have something a little more. We have more information now because we are not saying, okay, it's kind of yes or no. We are giving a whole range of values. And it's good. I think it's more information because you also know, you have a sense of the spread of the values. That with simply saying, okay, I pick 0.05 as my significance level, and then we keep or reject the null hypothesis. Here we say we can reject it, but we know how far we are, right? Because we have this kind of idea of this range of values, which is given by the confidence interval. So in a way, it's kind of going from a discrete decision to something that is more nuanced, because we might be wrong, but if the confidence interval is very wide, we might be very close. So if our confidence interval is very narrow, we are very sure that we don't contain that mean. But if it's very broad, then we are very close to not rejecting it. So it's more nuanced there. In looking at these results. So I'm gonna leave it there because we still have a whole other chunk of material to go through, which is also very important. But I think it's something that you might know more about. So you should be able to go quickly through it. So essentially. the next topic is statistical correlation. And here, well, first of all, what is statistical correlation? Well, correlation means that, I mean, we all have this intuitive concept. There's some association which doesn't mean causation. You know, the correlation is not causation. So we know that values between two variables are related with each other. You know, when one variable x increases, y also increases or decreases, but it's not like the variables are not kind of connected. So this is an example of what you would expect if variables x and y are correlated. You know, they change together in a way, which doesn't mean that one causes the other, but simply there is something, some mechanism that is making them to have this association in their values. They might be that x is causing y, but we don't know. This is kind of the other extreme. I mean, if x and y are independent, you would see like a cloud of points that don't seem any discernible pattern. And so, well, I guess this concept is fairly intuitive. How do we actually give a number? How do we calculate that, right? And there are many mathematical measures of correlation. Typically, they measure linear association. If variables have they have a linear relationship between them. And here is something like this. This figure is showing a range of possible correlations where you start from a very strong positive correlation, perfect association, where it's almost identity. Like if you have x equals y, you would get something like that, and you progressively get associations that are weaker until you are in the middle there, where it's completely there is no association. The distribution of points x or y is completely random, and then we can go on the other direction. But you see that in all these cases, the relationship falls along a line, right? And same, I would say, okay, that's in the top row. The other one is simply showing that the association could be linear, but with different slopes, right? So there are two things here. There is, in a way, how spread the points are, and also the slope, right? So we'll see how we capture those. The other thing is that that's why I mentioned linear association, because if you use a coefficient, a correlation coefficient such as Pearson correlation coefficient, and you calculate it on all these kind of associations that we have in the bottom row, they all would give something that is zero, or very close to zero. And the reason why is that the Pearson correlation coefficient will measure a correlation. It will be different from zero if there is a linear association. But if you give zero, you cannot conclude there is no association. It might be the case that there is a nonlinear correlation, but that is something that you cannot capture with this coefficient. There are other ways of quantifying nonlinear correlation, but again, something that is falling outside of the scope of this lecture. So more concrete examples, because this is kind of in the abstract. Here, if you look at obesity rates and actually density of fast food restaurants, you see a clear associations. So the more, with increasing number of fast food outlets, then you observe in that neighborhood, that area, increasing in obesity, and you might wonder what's the cause. But that's a complicated question, right? I think in this case the answer might be quite straightforward. But sometimes, going from correlation to causation is not. It is something that takes a much more nuanced analysis. But this only to give you an example. Clearly, there is a correlation there, which is linear. This is another example of linear correlation, and here you see that income inequality is correlated with life expectancy, and this is something that is. It's very clear to see here in this plot. I'm not sure if it's over the entire United States or a number of cities. I think it's around 500 cities in the United States. So it's quite representative about the effect of inequality. And this is an example closer to what you, I mean, very close. In fact, you've been working with this data. And here you see the correlation between this amount of interaction with receptors, cell receptors, and the generation by the cells of these cytokines. And there is clearly an association there. In some cases, seems linear. Well, you might say it's not linear because it actually seems to be following a curve. Maybe some range of the values have a linear association, but you see it's more like a curve relationship. So let's start with the Pearson correlation coefficient, which I guess is the simplest. And it as I mentioned, measures the linear correlation between two numerical variables x and y. And the definition is there. So rho. So here you have the standard deviations. So first the covariance. The covariance is a measure of how, in a way, the covariance between x and y. Again, without getting into the nitty-gritty, it's just the expected. So it's the kind of expected value of this kind of joint. Kind of, you see x. What you have there is kind of the difference between the values of the variable and the mean, and those are multiplied for x and y. So the sign of that, it would kind of, if variables change together, that expectation would kind of be either positive or negative if they go together, increase together or decrease together. But if they're kind of, if the variables are not associated, that expectation would be kind of be around 0. That's what's happening. And then you have kind of dividing by the amount of variation of each variable separately. And that's a value with that normalization. By dividing by the product of the standard deviations, you get something that is between minus 1 and 1. Well, I was saying that the covariance actually is something that we have this theoretical definition, is an expectation, but how we calculate expectation is a population a parameter, as we were discussing before, but we cannot, again, same problem before, we cannot go through each member of the population and calculate the covariance. We need to do a sample estimation, which is that. And as I was explaining, this measures whether x and y change together or not. And if they do, the covariance should be non-zero. And then, it's kind of this kind of tied, how they are connected, right? If the x's increase with respect to the mean and the y's also do the same, then you have a covariance that is greater than 0. And the other way around, if the relationship is linear, that's why when you have a non-linear relationship, then you might end up with a covariance that is 0, but that's because you have something that first goes up together and then they go down together and then they cancel each other, right? But as long as the association is linear, then we are fine. So how do we calculate estimates from sample data, right? So if we have a sample of pairwise xy values, we have the statistics. Essentially, in a way, going back. So when we're talking about parameter estimation, we only focus on the mean as the population mean. But this is another population parameter that we estimate. In the same way that our statistic, the term statistic is some formula that allows us to estimate a parameter from the population using a sample. And here we have a sample, and we just apply this formula. And it's kind of similar idea, right? It's that you put kind of what you have in the formula, in the theoretical formula that you would be able to apply on the whole population. You just apply the estimators, the sample estimators. And that is kind of approaches raw. And here you see that here you have the Pearson correlation coefficient in the very first one is very high. It's close to 1. This one is lower. Still, you might say, well, there is some amount of linear relationship. Here in the next one is negative. There is a strong linear association, but negative. And here is something that is even less associated. Not entirely 0, but pretty low. So this is kind of a little. I put this slide here because I wanted to draw a connection between confidence intervals of the correlation coefficients. In a way, kind of connecting the two topics, right? The calculation of correlation coefficients and the confidence intervals. And actually, we can calculate a confidence interval because, in a way, if I give you a point, if I give you a point estimate for rho, you might say, well, how good is this? What if okay, if I tell you, okay, the rho is 0.8, oh great, I have a very strong linear correlation, right? Linear association. But what if the confidence interval is actually super wide, like it almost reaches 0? So then you might not be so sure it is so great, right? So there, I mean, again, and there are formulas to do that. There is a way of defining in a very similar way as we did for the mean. There is a way of calculating a variable that has a normal distribution that tends to a normal distribution. It's calculated in terms of the sample estimates of the Pearson coefficient that actually give us a confidence interval. And kind of this idea of confidence intervals using the central limit theorem extends to many other parameters. And with that, well, there's a different way of calculating the standard error, but in the end, we can calculate the R, was R here? Oh yes, we recapture our, I think what happens here is that we do, I missed a little bit train of thought, but yeah, I think what we do is from our normal, from this variable z, we can capture, we can go back to R, which is the estimation of the Pearson coefficient. And that's what gives us, in the end, this estimation. So by using that, we have, let's see. Oh, see here, for the first one that had a very strong, you see what's going on. There is very little noise. I mean, the association is very, very, very clear. You know, there is, I mean, things are along a line with a positive slope, but also there is very little dispersion, and that is captured by the confidence interval. That's kind of a connection in a way. If we get away with something from all these, is that the confidence interval gives us a sense of that dispersion, right? The confidence interval is pretty narrow. You see that is 0.95, 0.99. So it's very, very narrow around 0.98, which is our estimate. And for this other one, the next, this one, you see that actually the confidence interval is very wide. It goes, from almost 0 to 0.7. So we really have little confidence. Even though the point estimate is 0.4, you might say, well, 0.4 not too bad. I mean, there is a, maybe not too bad, but actually it is pretty bad because the confidence interval is very wide. The next one is actually, it's negative, and maybe it's wider than the first one because there is more variation, but still pretty good, I would say. And then we have, in this case, something that definitely contains 0. It goes negative and then positive. So we don't know. We might actually have the true Pearson correlation coefficient might be 0 because it's contained. Is the possibilities that we could have with a 95% confidence might be the case that 0 is in this interval. So yeah, I think what else? So I guess I'm going through all of these connections between correlation and other things that are also very important, like linear regression. I think you saw that we are talking about linear association, and we have a very, and this is something probably you've seen before, where linear regression, if you have data points, we want to find the best fit line that passes through the data point. So we can write the y as this kind of linear formula, and something like this, right? We have this data set from before, and this other one also from the examples I gave earlier, and there's a connection. Obviously, it seems intuitively, if our Pearson correlation coefficient is close to 0, that would mean that our linear regression line might be horizontal. And well, we were talking about that, right? In a way, is more of the dispersion of those points. We saw that we can have we can have a line that has a very spread cloud of points, but when we do the linear regression, we still get a line with a high slope, but the points are all over the place. So that's measured by the Pearson, by RxY. And in this case, we have a dispersion that is not very high, and this one it is much higher because and also the sign for the amount of dispersion doesn't matter if we just take the square of Pearson. as I was saying, we have this idea of expressing y as a linear function of x. So then we can predict. So if we have an x value, we can predict y. And the idea of this, how we find the betas, which are the intercept and the and the slope, is essentially by calculating minimizing the error, the square errors, the sum of square errors between the data points and the line, and that's how we get these linear regression coefficients. And yeah, I think the interesting thing is that, well, we can reach formulas again. All of these formulas can be calculated very easily in code. But the interesting thing is that there is a connection, a strong here you have a connection between the Pearson correlation coefficient and this kind of slope, and where S, x, and y is are the corresponding sample standard deviations. And right, so I guess kind of feel like running through lots of things, but there are many correlation coefficients, and this is another one that I want to mention. I think is important because Pearson correlation coefficient, we use it when we have numerical variables, but that's not always the case. So we might have situations where variables are not like a continuous number, but we can. They're like ranked variables. They are also called ordinal variables, where we cannot say, well, they don't have like they are not numbers, but they can be arranged from smaller to larger. For example, and in that sense, for example, if we are thinking of the years in school, K through 12, each one is a rank. We just rank them, right? And in that sense, they are ordinal variables. But it doesn't make sense to add them up. It doesn't make sense to think of the years of the class year as a number. Say what is first, fifth year plus eighth year. They don't work as numbers in the sense that we don't do arithmetical operation with them. But at least they have an ordering. And so with this, there's also a way of defining, very similar to what we did with Pearson. There is a correlation that gives us this coefficient that we define in terms of the ranks. Which values come first in our sample, and then we can do this calculation. The ranks mean is the first, the second, etc. And the formula is kind of similar. And an example for that is like, in this case, this is a little bit of a, example from animal behavior, where they look at number of eggs of this nematode, and this is a number that that can be used to kind of compared to things that are ordinal. In one way, the dominance is higher as an ordinal variable because it's from less to from small to large, but it's not something that we can add up. And this kind of concentration of the kind of this number of eggs in the feces of the monkeys is something that measures. Again, in this case, it's just we are trying to quantify the infection by these nematodes, but in the end, these numbers we have them as a rank of the degree of infection of the animal by these worms. So in the end, one calculate what we do is we have a dominance rank that is an observational variable. That people look, the scientists look at this kind of level of dominance between in the hierarchy, in the social hierarchy of these animals, and then they calculated this eggs rank that gives a sense of how affected the animal is by the worm, and then they calculate the correlation, and that's something that again, the good thing is that we have the concept. We don't need to worry too much about the formulas that are there, but we have this correlation test in R, where the function is indeed the method so we can supply different correlation. We can specify the correlation that we want to use, and then that gives our estimate, which in this case turns out to be pretty close to 1. So yeah, I think the interesting thing about Spearman is that it can be useful for nonlinear relationships. That's kind of the thing that is interesting, because if we use person in a correlation in variables where the association is nonlinear, it might not be the case that it's 0, but we might be underestimated, because it's kind of trying to get a sense of the linear association, and we might have a very strong association between variables, but along a curve. So what we can do, that doesn't affect Spearman, because for Spearman it's only kind of this ranking, and that's kind of less affected by this nonlinearity. And in that sense, we could have relationships that are monotonic, nonlinear, monotonic, and but won't work is if we have something that increases or decreases. But we can use Spearman to measure association in situations where the association is not just along a straight line. Yeah, so that's. I know that this last part was kind of a little of a rush, but hopefully you got basic concepts, and with Sarah during the workshop you will be able to apply all of these methods, and yeah, I think it's gonna be a great session overall, both with all of these concepts we learned today and the applications, practical applications. So some references here, and finally, these are the reading materials that I mentioned throughout the lesson. So thank you so much.